Today's topic is time dilation. We have already seen that where the speed is very less than the speed of light, then the special relativity or relativistic and Newtonian mechanics, they agree. But as soon as we talk about higher speeds, then Newtonian mechanics fail and we have to replace it with relativistic theory or special relativity. Time dilation is nothing but it says that a moving clock ticks more slowly than a clock at rest. So if two events are happening simultaneously on Earth or on the ground, and those events are happening simultaneously on a spacecraft or a spaceship which is traveling at a very high speed, then it will be noted that the time interval measured between the two events, it will be quicker on Earth, whereas the time measured for the same events happening in the spacecraft, it will be dilated. Dilated means it will be stretched. So time or the clock which is in the spacecraft, which is going at a very high speed, it will tick more slowly than the clock which is at Earth. So in this video, we will be doing the derivation which is required to generate the formula for time dilation. Alright, before diving into the derivation, we need to know a couple of things. What is proper time? In this derivation, we will denote proper time by T0. Proper time is the time which is measured when the observer and the events for which we are measuring the time are in the same frame of reference. What does it mean? If I am on the ground and the events are happening on the ground, then yes, the time I will measure will be called proper time. If I am on the earth or ground and the time which I am measuring is happening in the spacecraft for the events, then it will not be a proper time. Alright, so observer and event happening are in the same frame of reference. This is an important point to remember, that what is proper time? When the event that is happening and the observer, they are in the same frame of reference. In the following derivation, which I will show in this video, observer is on the ground and therefore the time which will be measured on the ground, it will be denoted as T0. Alright, so let's now dive into the derivation. Let's see the construction of the clock which we will be using for this derivation. Now this is a thought experiment. Thought experiment is something which we think. These kind of experiments have been done, but this one is a thought experiment. Alright. This is the clock that we will be using in our derivation. How does this clock work? There are two mirrors, mirror 1 and mirror 2. The distance between the two mirrors is L0. Okay. The lower mirror is attached to a recording device. A light pulse travels between these two mirrors. Let's say it starts from mirror 1, goes to mirror 2, comes back and hit the mirror 1 again. As soon as it makes the round trip, it records a tick. So what is the tick? When the light pulse travels from mirror 1 to mirror 2 and back to mirror 1. Alright. Now this is shown in the second part. On Earth, how will we record it? On Earth, what are we recording? Because the observer is also on the Earth. So we are recording proper time. So we will be talking about T0, T0. Okay. Let's say this is mirror 2, this is mirror 1, mirror 2, mirror 1, mirror 2, mirror 1. The light pulse, it starts, it hits, okay, that is the time T0 by 2. Why? Because the time is a tick T0 when it makes a round trip. That is in here, okay. The main thing to note is that the distance traveled in this part will be L0. When it makes a round trip, distance traveled will be 2L0. What will be the speed of the light? The speed of the light is, we all know, c, distance divided by time. If I am taking the distance as L0 or L0, I will take the time as T0 divided by 2, or simply I can take the distance taken as 2L0 and time as T0. Alright, so C equals to distance over time. Which formula I am using? Very simple. Speed equals to distance over time. Let's rearrange this equation. T0 will be 2L0 over C. We will call this equation 1. Alright. Now let's draw a similar diagram for when the same clock has been in the spacecraft. Okay. So let's say that we have built 2 such clocks. One is on the ground in the laboratory with us and another one is taken in the spacecraft, which the person who is on the ground will observe. Alright, so the person on the ground should observe time being dilated, time being stretched, and therefore the clock which is on the spacecraft should move slowly. Let's see. Now on spacecraft. Let's see, this is mirror 1. I'm making it shaded for a reason. Let's say now I have here mirror 1 and this is mirror 2. I am in the spacecraft. You are on the ground observing me going very fast. Okay. So when the light will start from lower mirror, mirror M1, by the time it will reach M2, this part would have moved forward, right? So what the person on the ground will observe, that the light is, rather than traveling up straight as he observed in the laboratory within the same time frame of reference, he will observe the light going like this. Because till the time the light will reach upper mirror, the spacecraft would have moved forward. Now this is the new position of mirror 2. When the light will bounce back or reflect back from mirror 2, it would have moved further. So on and so forth. So zigzag pattern will be followed when the observer is on the earth and the clock is in the spacecraft. Alright, let's do the further derivation. Continuing with the derivation. Now, this, when the light reaches to the upper mirror first time, the time will be T by 2. We will not use T0 because this is the dilated time, not the proper time. And let's say V is the velocity with which the spacecraft is moving. So what I have done here, to find out the distance that the light has traveled diagonally or in a zigzag manner, distance equals to speed into time. Simple formula. So this time we are measuring for the light pulse. So speed is C because it's a light pulse. So it will travel with the speed of light. And the time will be T by 2. Alright. This is distance between the two mirrors. That will be L0. This is the distance, speed times time again. But this time the speed will be the speed of the aircraft with which the speed with which the aircraft is moving. So it will be V times T by 2. Now using Pythagoras theorem, we will do some algebra with these. So hypotenuse square equals to perpendicular square plus base square. This is the hypotenuse square, perpendicular square and base square. So this is CT over 2 square, perpendicular is L0 square, and plus this is VT by 2 whole square. Alright, let's Let me have some. If you want, you can pause the video, draw the diagram, do it yourself. More than happy. Let's draw it a bit down. D by 2. Okay. I'll bring this over here. So it will be c square t square by 4 minus v square t square by 4 equals to L naught square. I can take t square by 4 common. It will be c square minus v square equals to L naught square. Alright, I'm rubbing it off completely. I don't have space. Alright, now can I write like this? T square by 4 c square 1 minus v square by c square equals to L naught square. Taking square root left hand side as well as right hand side. T by 2 c 1 minus v square by c square, that will be whole in under root, equals to L0. Alright, then t will be 2L0 divided by c 1 minus v square by c square. Alright, let's name it equation 2. We are getting very close to the formula for time dilation. Alright. Remember, we had an equation 1, that is t0 proper time equals to 2L0 divided by c. So from this we can say 2L0, move this c to here, so t0 times t. Now let's put this value of 2L0 in our equation number 2. So what was my equation number 2? It was t equals to 2L0 divided by c under root 1 minus v square by c square. Let's put this here, value of 2L0. It will be t0c divided by c under root 1 minus v square by c square. I can cancel c with c. So t equals to t0 over under root 1 minus v square by c square. Now, just to simplify, we can put 1 divided by root of 1 minus v square by c square as gamma. This is also known as Lorentz factor. And this will be used many times when we will talk about twin paradox, length contraction, time dilation, and different phenomena related to special relativity. So maybe try to remember it. Gamma equals to 1 over square root of 1 minus v square divided by c square. So if we put this in this equation, t equals to t0 gamma. This is nothing but the equation of time dilation. This one or this one, both are. Alright. Now what will happen if the observer was in the spacecraft and he was observing the similar clock on the earth? He would have found the exact same thing. For him, time on earth will go slower, because for him, he is in another frame of reference than what he is observing. Alright, for him, he is just in the spacecraft and earth is moving away from him. So the same, he will get exactly the same mathematical formula and the same observation, that for him the clock on earth will tick slowly. Alright, this is about time dilation. Couple of things can be found out from the Lorentz factor. Let's say 1 minus v square by c square square root. It will always be less than 1. Why? Because v is always less than c. If v is less than c, then this is always less than 1. 1 minus something which is less than 1, square root will be very small. Okay? Can v be greater than c? Lorentz factor gives us a very important thing in physics, that can anything travel faster than light? Let's say if v is greater than c, then what will happen? 1 minus 1 point something, because v is greater than c, it will be square root of negative. That will go into iota or imaginary number, which cannot be mathematically quantified. So therefore, maximum speed which can be attained in this universe is speed of light. That is the speed limit of anything. Alright, so this gives us that nothing can travel faster than light. This was the whole derivation about time dilation. There are many questions which can be done on time dilation. In my next video, I'll try to solve some of those questions. Thank you.